Well, welcome to tonight's GMAT free prep hour. It is April 14th, the eve of tax day here in the US. My name is Whitney Witt. I'm a GMAT GRE and executive assessment instructor here at Manhattan Prep. And tonight I'm excited because we're going. I kind of was in the headspace the last few free prep hours to talk about some of the more archetype questions. So, in the last several months, a couple of things that I've talked about are like unit conversion questions, distance rate time questions, work rate time questions, and even overlapping sets. And so I thought, you know what, let's carry on with this kind of tradition of the questions on the GMAT that have a really clear flavor, like a really clear style of their own, and that along with that style have a very like a sort of limited set of solution methods that we are likely to use. So we are this evening going to work on a Quant and Data Insights topic known as weighted average. So it's part of the statistics averages family, but these in particular deal with what happens when we've got like two subgroups and then those groups are combined. Yeah. So let's take a look. Let me go ahead and share my screen. I'll get us going. So in this world, right, welcome again. In this world of weighted averages, what's going to be really important is learning how to recognize that we're dealing with a weighted average problem type. So let me just give you a problem. Right? It's just going to feel like, any old sort of math problem. And then I will, let's say 2 minutes on the clock. I'll I'll check in at the end of 2 minutes. Pull in when you've finished. And if you're here live with me, if you'll type to me in the chat window how you solved this problem, what method you used to solve it. Okay, so that's about a minute and a half. And if you are on the recording and you're still working, feel free to hit pause. But let's go ahead and chat about this one. So we've got a scenario where we're clearly talking about averages because the question says the word average. Generally, I'm going to look at answer choices first. And so I've got answer choices that are all whole values. They're all kind of in a compressed range between 92 and 98. And as we read the question, we're sort of introduced to like Anna and a quiz grade. So of her first, like 12 of these quizzes, her first 12, she scored 100. And then we find out that a second 12 of them, she scored a 90. And I want to know what her final quiz grade is. Now, if I'm thinking formal math weighted average, it's important that we understand what the weighted average formula is. So the way that we would calculate weighted average, again, formally, would be I would take the average of one group, so like average one, and I'd multiply it times the weight of that group, like the size of that group. I would then add that to the average of like my second group or second category, and I'd multiply it times the weight of that average. And then I would divide this whole thing by, the sum of all of those weights. In essence, this is, if we think about the average for a whole group, this is the same as the total sum divided by the total number of terms. Now, when we're dealing with averages where we've got like a bunch, they give me a whole list of numbers, right? So if they had told me individually a bunch of her tests, she scored a 92, a 91, a 90, a 94, another 94. We're not necessarily going to use what we would call a weighted average formula. We would just add up all those numbers and then divide by the total number of tests. We move into the world of a weighted average when we've got essentially we're bringing together, at least on this test, two different subgroups. And then we want to know something about the average as a whole of everyone together. So the average of her first tests, the average of her second test, what's the average of all of the tests when they're brought together. Now, formally, multiplying all this out, I could say, she had a score of 100 times 12, plus she had a score of a 90 times 12, and then I'm going to divide that thing by 24. Thing that's annoying here is that this is a part of the test, right? A multiple choice question like this is going to be on the quantitative portion of the test where I don't have a calculator, right? And so why would they be giving me something where there's just like this many, not the most beautiful numbers to manipulate? And it's because weighted average doesn't really care how many tests we take or how many total, right? This sum, this number down here, it doesn't really care about the actual values of these weights. In fact, all it really cares about is the proportionality. And let me show you what I mean. If I were to factor a 12 out of both of these terms on the top, I could then factor a 12 out of this 24 on the bottom. And what we find is that in order to get the weighted average of this particular problem, it's in fact the same as the simple average if I took 100 plus 90 and divided it by 2. The reason for this is that when we're thinking about the weights of subgroups, we don't actually care what the actual weights are, just what their proportional weights are. So the fact is that half of her tests, she scored 100. An equal half of her tests, she scored a 90. So each of these subgroup weights will have an equal weight on the overall average. The 100 and the 90 will be equally weighted when we calculate her average. And it's why her average is, in fact, halfway between the two at a simple 95, the halfway point between 90 and 100. So the fact is that at any point we could have said on 2 of her quizzes on the other 2, on 27 of her quizzes on the other 27, on half of her quizzes on the other half, she scored a 90, she scored 100. What was her final quiz average? Boom, right in the middle. I want to start cultivating a visual that will allow us to bring kind of real math principles to more of an estimating technique for weighted average. And the way I do this is sort of a tug of war, right? Like process. And generally, it's going to have the following form. So the form has space for 5 different input values. Okay, so what we'll do here is think about this line here in the center as a bit of a tug of war. We'll put one of our groups on the left, we'll put another one of our groups on the right. And I do like to keep my values kind of in line with how an average formula would work. Up top is where I'll be putting the value that we're averaging. That'll be all of these boxes at the top. And at the bottom will be the number or the percentages, the weights, if you will, at the bottom. So the way that we would look at this problem is that she's got 100 on 12 tests. She's got another 90 on 12 tests. If I know both of my inputs, then I can take the numbers and I can reduce them to their lowest proportion. So a 12 to 12 is the same as a ratio of 1 to 1, which means this end and this end are both pulling in equal amounts. So the average would land dead in the center. And so in this case, the number dead in the center would be 95. Our correct answer is C. Okay, so given that we know this, that if my two subgroups that are coming together to form one big group, right, if those two things are equally weighted, if they are the same size, the overall group will look like the thing in the middle. Okay, so what happens if we change the problem slightly? All right, so that's just about 2 minutes. So again, feel free to pause the recording if you're still working. So I would set this bar up again. Again, part of what we want to look at is how do I recognize this as weighted average? We've got 40% of her quizzes, she's got one metric. On 60% of her quizzes, she's got a different metric. So what was that same metric, meaning score, average, grade, right? What was that if I bring both groups together? So I'll kind of build my little form. I've got 40%, she got 100. On 60%, she scores a 90. Now, the first thing I'll do here is say, all right, I'm going to reduce these 4 to 6 or 2 to 3. So keep reducing my ratios. So I got essentially 200s and 390s. If you wanted to, you could plug these into the formula right now, right? 90 times 3 plus 100 times 2 divided by 5. Fine. But the first thing I'd like to do, especially with multiple choice questions, is use a process of elimination if that's available. So what I'd note is, all right, if I'm given my two input ends and what I'm missing is the middle, the first thing I do is ask what would happen if these two groups were in fact equal. We already know if these two groups were actually equal, the score would be a 95. Well, I know that they're not equal, so the score can't be a 95. I also know that the grades of 90 are going to have a bigger impact on her score because she had more of them. So that means that Anna's GPA, right, her overall final quiz average, is going to get pulled towards the 90 end of things. So I know that it can't be a grade above 95. And so I will eliminate either of those. Now I can stop here if I want, but what I want to highlight for you is that this kind of tug of war, right? The 3 end is winning, it's pulling more in its direction, can actually be translated to an exact ratio to figure out the difference. So, one of the things I can do is say, all right, the 90 has a strength or a weight of 3, meaning that it is pulling the average 3 in its direction, like 3 strength, so to speak. What I know is that the hundreds only have a strength of 2. And so it's essentially pulling 2 units its direction. Now, one of the things I can then kind of use this ratio to extract is that if this whole distance is 10, 3/5 of those pieces are going to be how far it's pulled away from 100. 2/5 of those pieces is how far it's being pulled away from 90. Another way to think of it is I can split this line into like 1, 2, and then I split this one into 1, 2, 3, right? This should have 3 blocks. This has 2. I split this line into 5 blocks. I can draw this out like a number line. So if there are 5 blocks to get me from 90 to 100, each of those blocks is worth 2, right? Because I would go 90, 92, 94, 96, 98, 100, just like on a regular number line. And so I know that if the actual place where these are meeting is right here, then if I were to mark these lines out, this is 90, this is 92, right? 94, 96, 98, the actual average is 94. You might have also been able to estimate this because I know that the tests where she got a 90 are stronger, but they're not so much stronger than the tests where she got 100, that they're pulling the average all the way down to 92. There'd have to be a much stronger weight there. It's only a 3 to 2. They're only slightly more heavily weighted. They're about 50% more heavily weighted than the hundreds. And so a good guess would even be something closer to, say, 94. But we can get there mathematically as well. So if I know my endpoints, I can always reduce the weights to their lowest ratio. I can always compare what the actual 50/50 would be and kind of estimate where the real average would be. Or I can even mark off tick marks on my line, so and then fully calculate where that piece is going to be. Okay, let's see what happens when what's missing is something on one of the ends. How can we go about using this same kind of pull and push to do that? So let's give this one a go. All right. All right. So let's take a look at this piece. We're still in the same format of overlapping or of weighted average, right? I've got a final quiz average. It feels like kind of an overall. But then I'm subdivided into two groups. I've got the first six and then the rest. Okay, so I'm going to sketch out my over under. I'm going to put this one in a different order. I'll put the 90 on the rest. So I'll do them in order ascending this time. It doesn't actually matter. And then I have 100 on my first six. I'm told that my average score was a 96. And I'm trying to figure out how many tests did she take in total, which would be this missing number. What I'm solving for is x plus 6. Well, here's what I know. If she took 12 tests in total, that would be an even number, and she didn't take an even number because this number is not in the dead center. So if anything, I can kind of eliminate that. I also know that she must have taken more tests where she got 100 because it's to the right of my average, right? My average would be 95. So it has to be, this number here has to be something less than 6. So it can't be anything more than like 5, but that doesn't, doesn't really account for the rest of these, although I know it's not going to be 0 or negative. So I can get rid of A and B, right? She can't take 4 tests in total if she took 6 where she got 100. Those two won't work. So it's either that she took 2 or 4. You could certainly, 2 down here or 4 down here. You could test that out, but let's use the sort of tug of war to actually solve it. So one of the things I can do is say, all right, she pulled in both directions. So the 100 is strong enough weighted that it pulled this all the way up 6 from the 90. She was able to pull the average 6 up towards the 96. On the other end, right, whatever's down here was able to pull the average 4 in its direction. So this ratio 6 corresponds to this end, while 4 corresponds to this end. We have a kindness in this one because the 6 already matches. I don't need to convert anything from my ratio. Note that I could have converted this from like 6 to 4 to 3 to 2. I could double them 12 to 8, any pairing of these. But these are going to be in a ratio of 6 to 4. I've already got my 6. This end will be 4. For a total number of tests, D, 10. So it doesn't matter what pieces I'm missing. I can still use this kind of pull over under to figure it out. So I can find the middle number if what I know are the outer two. I can find one of the bottom numbers if I know the rest. Okay, let's try one more variation before we start to get into some more challenging versions of them. All right. If you haven't given me an answer, please do. And again, if you're watching the recording, feel free to pause. So again, we know this is in the same format as the last few have been. So I'm just going to go ahead and set them up. Okay, as we get into some new looking questions, we'll talk about how to recognize. So I've got, she earned an average grade of 90 on her first 10. So that's going to be some sub portion. So 90 on 10. And what must she average on the final 5? Okay, so what's missing is the other average. Right? And in general, she wants to earn a 92. I don't really know where this goes, so I'm going to stick kind of the 92 up here for a second. That's her actual average. What I know though is down here, 10 to 5 is the same as a 2 to 1. I can in fact mark this as a 2 units pulled towards the 90, while there's only 1 unit pulled towards whatever number this is. So if I think about this as 2 units, 1, 2, and this piece is just the 1 unit, this is where the 92 would live. So if 1 unit represents 2 points from 90 to 92, then this would be 94, and this will be 96. Count them up. And so I can get to that end of my average pretty easily. Okay. Questions on setting up the sort of line? Okay. All right. So let's add some wrinkles then, shall we? Let's give this one a go. All right. How did this one feel? Easy? Medium? Okay. Yeah, I feel that too. Yeah. Okay. So we're looking at, you know, 40 cars in the lot, and then we get some new cars, another 80. We want to know, okay, this new bigger group. Yeah, okay, we're talking overlapping sets again. So we'll start with our kind of the tug of war. And what we're comparing, let's just get really clear, is that we want percent of the total number of cars that are silver. So I might make a note to myself, this is percent silver. So of the original 40 cars, 30% are silver. Of the new 80 cars, 40% are not silver, which means 60% are. Let me reduce this. The ratio of 40 to 80 is 1 to 2, which means this end is pulling 1 unit. So the 30, right, is pulling 1 unit in its direction. The 60% are pulling 2 units in their direction. At a minimum, I know that the answer has to be higher than 45, right? So I could do an estimation here because the midpoint where they were equal would be 45%. So I know the real answer has to be to the right of that. But I can calculate it exactly as, right, if I were to break this into 1, 2, right, this gets broken into 2, and this is just 1. So I break this length from 30 to 60 into 1, 2, 3 segments. And so these segments, if I were numbering them on a number line, would be 30%, 40%, 50%, 60%, which means my correct answer has to be 50%. Yeah? How we feel? I want to grade from 0 to 5, 0 being the least comfortable, 5 being your most comfortable with setting this up. How is this going so far? How do we feel? 0 to 5. Cool, not bad. All right, well, then let's build the challenge. Here we go. Let's try again. And then we're going to switch over and do some data sufficiency and some two-part questions. And then we may, if we have time, look at what to do when variables get included. All right. So let's take a look and try to identify, like, how are we meant to know that this is a weighted average problem? So a convenience store currently stocks 48 bottles of water, and they have them in 2 sizes, 20-ounce sizes or 40-ounce sizes. So two different types of bottles. And then we have the average volume per bottle is 35 ounces. So if the average volume per bottle is 35 ounces, then I know, right, that if I've got, let me think of these ones down here as like, right, the average of my 20-ounce bottles would be 20 ounces. The average of my 40-ounce bottles is 40 ounces. So if I had one 20-ounce and one 40-ounce, for example, same size, right, or 50-50, 24 and 24, then my average volume would be a 30-ounce bottle, right? 120 and 140 would give me 60 over 2 or a 30-ounce bottle. But, right, so where they're equal would be 30. However, the actual number is 35, closer to the 40 ounce. So what I can look at is that I'm being pulled 5 on this end. The 40 ounce is pulling 15. That gives me a ratio, right? So it's like for every 15 40-ounce bottles, I have 5 20-ounce bottles. In other words, I have 3 times as many 40-ounce bottles as 5-ounce bottles. I'm going to reduce this ratio. This is a ratio of 1 to 3, right? 3 times as many. So out of every 4 bottles, 3 out of 4 are 40 ounce, 1 out of 4 are 20 ounce. I have a total of 48 bottles. So let me scale this up. I multiply 4 by 12 to get to a 48 bottle total. I can then scale this whole ratio up by also multiplying by 12. I'm just going to confirm it. Right, this would be 36. Over here would be my 12, which would still be pulling in a ratio of 1 to 3, right? 5 to 15. And so how many 40-ounce bottles are in stock? 36. I for sure know the answer is above 30, right? It's got to be bigger than 30. It's got to be bigger than 24. It's got to be more than half, because that's my half. And so it definitely can't be A or B. But if you can start to look at this like push-pull, you can solve and get to an actual answer. You don't just have to estimate. Okay, let's try a couple more. See how they go. Okay, the set took a little bit longer. So set S contains 4 numbers, and the average of all 4 of those numbers is 12. But then we add a number to the set, and that brings the average down. Okay, so I'm going to say that I had an original set of 4 numbers whose average was 12. We're going to add 1 number to that set. I don't know the value of that number, but I do know that it brings the average down to 10. Right? So I don't know where to put that yet. But what I do know is this is already reduced 4 to 1. I'm pulling 4 in this direction. 1, I cut this into 4 segments. 2, 1, 2, 3, 4 segments in that direction. And we're pulling only 1 segment in this direction, which puts my value at 10 right here where they meet. So what is the value of each segment? If this goes from 12 to 10, then each segment is 2 units. 10, 8, 6, 4, 2. So as we think of a weighted average, I want you to start to think of this like visual pulling. Right? Let's go with one that's quite a bit heftier. Takes a little bit of thinking, but man, these numbers, not pleasant. And then we're going to try out a 2-part problem, one of the DI family of problems. Here we go, but let's get this one go first. All right. So notice that we have, again, like 2 types of subgroups. We've got days on which Tom splurges, and we've got days where Tom does like the actual precise guidelines. But then we get an average calories for the whole 10-day period. So it's like subgroup, everybody combined. And so if we start to build this out, if I think, all right, he follows the rules, right? So on the days where he follows the rules versus the day he splurges. Well, on days that he follows the rules, he has 2,400 calories plus 200 calories. So that's 2,600 calories. On days he splurges, he has 3 times the recommended number of calories. So that would be 600 plus the 2,400. So on those days, he has 3,000 calories. Now, I know that whatever these two are has to add up to 10 days. So what I need to figure out first is their ratio. So 2720, I mean, if I were to look for the halfway point, we've got 400 between these two. So like 200 would be the halfway point. So they'd be equal if it were 2,800 calories. He came in under that, so it's definitely getting pulled in this direction. So the days that he splurged has to be smaller, right? It's being pulled towards the days he follows the rules. So he's going to splurge on fewer than half of the days. So at a minimum, I can guess that it's A or B and call it a day. However, let's go ahead and enter in the actual number. So the actual caloric intake was 2,720. So I'm just going to stick it over here to the left a little bit. The distance on this side that's pulling here is 120. The distance on this side that would pull here is, well, I take 80 to get up to 2,800 and then another 200. So this is 280. So these are in a ratio of 280 to 120. Knock off the zeros. Yeah, I'm going to divide both by 4. This is a ratio of 7 to 3. Oh, well, that ratio already adds to 10. So I calculated the ones I need. He splurged on 3 days. He followed the rule on 7. And we've solved it. Yeah. So note that we almost simultaneously solved for the number of days for rules and splurges because we were looking for relative proportions. Okay, so this might show up on the DI section of the test in both 2-part problems and data sufficiency. It could also show up in plenty of other questions, but these are going to be the most common places where we might see weighted averages. So I wanted to start with a 2-part example. The way a 2-part problem works is that you'll have question information up at the top. You'll have instructions for how to answer for each column. And you will answer a single answer for column, let's call this column 1, and another answer for column 2. So you would answer like A, C, right? Or C, C. And it is possible that the 2 answers are the same. Now, again, we're looking to take about 2 minutes. For these types of questions, we actually up the average. We say about 2.5 minutes. So enjoy. Give this one a go. Okay. So how did this one feel? Good, bad, easier, harder, iffy? Okay, fair. So I know this is a weighted average problem because we're talking about mixtures, and mixtures are going to always fit into weighted average problems. And so let me start by just sketching this out. I've got a line where I've got X is the lighter copper, Y has more copper. X is 25% copper by weight, Y is 65% copper by weight. And they don't give me anything else. They don't tell me how much of either. They don't tell me what my outcome is. So the question becomes, how am I supposed to answer this? Well, something common in the world of two parts is this jointly consistent style of problem, which means I have to solve the two questions at the same time. So there are lots of different answers. For example, if what I knew was that it was a 50-50 mix, right? If there were an equal amount, right? So 50% of it was alloy X, well, then how much copper would I have? I'd have the exact average of 65 and 25. So it's half of 90, add them together. The exact average would be 45, right? However, I have a 50% of X, but I don't have a 45% that I could choose for the amount of copper. So I'm going to start to use process of elimination. I'm going to write A, B, C, D, E, F in 2 columns on my paper with X over the first column and copper over the second. And I'm going to start marking out options for what it could be. So I know that it is not 50% of alloy X. What I know, though, is if I increase the amount of alloy X, the percentage is going to get closer and closer to 25. In fact, if I had 100% X, the percent of copper would be 25. Well, I don't have 100% as an option, and so 25 can't be an option for column 2. Same, I don't have a 0%. If there were 0% of X and 100% of Y, it would be 65. So I know that copper can't be anything at or above 65. So I'm going to eliminate both of these. Now, I've got some ugly numbers left, but 2 of the ones that feel a little bit better are this 25% and 75%, because the quarters correspond to these 4 lines. This is the line where 50% would have pulled toward X. This is the line where only 25% would have pulled toward X. And this is the line where 75% would have pulled toward X. And so I'm going to calculate the numbers that are halfway between these, because it's actually pretty easy to do. 25, 35, 45, 55, right? So here's my 35%, 45, 55%. So I don't have a 55%, right? And 55% would represent if I'd only been able to pull 25% in my direction. So I can't have 25% of alloy X. So, and I know I don't have 50% of alloy X. So let's see what would happen if I had 75% of alloy X. If I had 75% of alloy X, I would have 35% copper, and it turns out that I do, in fact, have those numbers. So if I had 75% X, I'd have 35% copper. If that one didn't work, right, if I didn't have a 75 or didn't have a 35, I'd eliminate those. I'd test out one more. I cannot imagine that they would make me do any of the uglier ones. Right? The test is going to let me get to an answer using the easiest answers or using the easiest checks to test. So my correct answers, F and then B. Yeah? All right. The other type of question that turns up in data insights that this could be more commonly seen on is the data sufficiency question type. And so I wanted to offer up an example of a data sufficiency question. So note that data sufficiency is asking us, right here are your 5 answer choices. Data sufficiency isn't about getting an answer, like figuring out what the answer is, but instead about trying to determine whether we can answer the question with the given information. So we're trying to figure out, can I get there with statement one alone? Can I get there with statement two alone? Do I need them together? So on. So give this one a go. We generally want to spend about 2 minutes. All right. If you haven't given me an answer, please do. Note that for data sufficiency, we are often trying to find the minimum amount of information necessary to be able to answer the question. What I know is that we're dealing with a weighted average, right? As soon as we recognize that, we've got the average of one subset, and the test does still do gender binary, but we've got the average of one subset, women, the average of the other subset, men, and we want to know what's the average of everybody in the room. Well, here's what we know now. We know now that in order to have the answer to this question, all I need to know are the relative proportions. I don't actually need to know how many men and how many women. I just need to know how many there are relative to one another. Are they the same? Are there twice as many, half as many, right? Like, what's that ratio? Statement one gives me the ratio, that the ratio is 2 men for every 1 woman. I could write out my bar. I've got 2 men at 150 pounds for every 1 woman at 120 pounds. And so this two, right, it pulls its direction two. This only pulls its direction one. And so I can calculate, this is 120, 130, 140, 150. I know what the weighted average is. No, you do not have to draw this out. Okay. Simply knowing, oh, I just need to know the proportions tells me that statement one is sufficient. It's enough information. If statement one is sufficient, I can eliminate B, C, and E. I'll check statement two by itself. Knowing the total number of people in the room doesn't tell me the breakdown of my two subgroups. So statement two is not sufficient. And so my correct answer is A. So, excuse. It is often enough in the world of data sufficiency to just understand, how does weighted average even work? We don't have to go through all the math. What we need to understand is, oh, I need a ratio of my inputs of my groups, right? Or I don't have enough if I don't have this piece, so that it saves us a ton of time in terms of actually solving. So now that you've seen some overlapping sets with these kind of push and pull, I hope that you look for more opportunities to apply this in practice questions in your official guide or on practice exams, maybe even the real thing. Please come hang out with us. You can come and attend any of these free prep hours whenever you'd like. We also have plenty of other free resources. So if you join us on our, ManhattanPrep.com, GMAT class is free. You can attend any session one of our full 9-week course. We've also got foundations of math workshops that are free. We've got where you can sit and meet with MBA mission consultants, right? We've got all kinds of free events on our website. So please come and hang out with us. Thank you so much for sticking around. It has been amazing to get to work with y'all this evening. Take care and best of luck on your exams.